In my first year of university, I did not like calculus. That might have been partly due to the fact that this epsilon-delta definition just made no sense to me. It wasn't until 2 years later that I took a course in metric spaces, and then it made much more sense. So actually, this definition looks scary, but in fact it's quite simple, and I want to show you how. In this video, I want to do 3 things. I want to come up with the epsilon-delta definition ourselves, basically from scratch, and I want to do some visualizations, and then I'll do a quick example to finish off. So let's jump in. So you might know the limit intuitively as the limit as x goes to a of f of x equals L means something like as x approaches a, then f of x should approach L. So approaches means something like it gets close to. But I can push for even more clarification and ask, what do we really mean by close? To talk about closeness, I need a notion of distance. So that begs the question, what is the distance between two numbers x and y? I want to split this into 2 cases, and you might see why when I draw this. But if x is less than or equal to y, then let's plot them out on a line. So that means that x is on the left and y is on the right. Then the distance between them is the length of this line between them. And we can probably see that that's y minus x. So the distance between x and y in this case is y minus x. For example, if x is 3 and y is 7, then the distance between them is 7 minus 3, which is 4. And that checks out. Okay, but if x is the larger one, then I need to plot it on the right. So in fact, the distance between x and y will be x minus y. Just for example, the distance between 7 and 2 should be 7 minus 2, which is 5. So again, we're just taking the larger one minus the smaller one so that our distance is always positive. Okay, so in general, let's say the d of xy, which just means the distance from x to y, is either y minus x in the case that x is smaller than y, or it's x minus y if x is larger than y. Okay, but you might recognize this as the same thing as the absolute value of y minus x. And that's a remarkable observation. So the distance between x and y is the absolute value of y minus x. So try a few examples of numbers for yourself just to check that that is in fact the case. Okay, so let's return to our question about closeness. So now we can say that f is close to L if the distance between f of x and L is small. So in other words, if the absolute value of f of x minus L is small, because the absolute value of f of x minus L is the distance between f of x and L, as we just saw above. Or we can be more mathematical about it and say the absolute value of f of x minus L is less than some small number. Okay, so similarly, we can say x is close to a if the absolute value of x minus a, which is just the distance between x and a, is also less than a small number. Okay, I don't just want it to be less than some particular small number. I want these to be as small as we like. So I'm going to need some variables here to help control these. So let's see if we can put the logic of the statement together. So again, for our limit, we want f of x to get close to L as x gets close to a. And we can write that as, for any small number, let's call it s, there is a threshold of closeness, we'll call it t, such that whenever the absolute value of x minus a is less than t, so in other words, the distance between x and a is less than t, we have that the distance between f of x and L, so the absolute value of f of x minus L, is less than s. So x is within our threshold of closeness to a, and that should imply that the distance from f of x to L is smaller than our small number of choice. So let's trim the fat off this a little bit, streamline it. So the limit as x goes to a of f of x equals L means, so far, that for all s greater than 0, there is some t greater than 0, such that if x minus a is less than t, then f of x minus L is less than s. So s being our small number, and t being our threshold of closeness. Okay, so one last thing I should point out, that for limits, we don't actually care about what happens at x equals a. We're allowing for holes in our graph. So we're going to omit when x equals a, and that just turns into x minus a, an absolute value, is strictly greater than 0. Because if it was equal to 0, then x equals a, and we don't care about that point. Okay, so let's try to visualize this. I'm going to draw a graph, and let's put a hole in it at some point at x equals a. And let's say the value of that hole is our limit. So the definition suggests that we should start by picking a small number s, and we want that to be small so that we get f of x to be close to L. Okay, so that means that absolute value of f of x minus L should be less than s. But that turns out to be true exactly when f of x is between L plus s and L minus s. So to check that, you just get rid of the absolute values. You get two inequalities and you move the L around. So check that for yourself. Okay, well, we can draw L plus s and L minus s on our y-axis. And let's extend these lines out. So in particular, f of x minus L in absolute value is less than s when the graph of f is between these orange lines. Now our goal then is to find a threshold t such that whenever x is within t of a, so in other words, the absolute value of x minus a is less than t, or x is between a minus t and a plus t, then the graph is between our orange lines. Okay, so if we pick a t that's too large, let's just put it way out here, these pink lines. So notice that this interval is a minus t to a plus t. So x being in here means that the absolute value of x minus a, or the distance between x and a, is less than t. We see that this is too large. The graph of f of x in this interval can escape our orange lines. So this is too large of a region. But if we pick t to be smaller, then we see that the graph above that interval is completely contained in the orange lines. So this is a valid threshold of closeness to make sure that our function is close to our limit. So in other words, we need to pick t that's small enough to work. Okay, so our next problem is that we also want to be able to shrink s. It's not good enough to say that it's within some fixed distance from L. We want it to get arbitrarily close to L. But this might entail shrinking t in lockstep. So if we shrink s and we can't find a t that works, then we can say that the limit actually doesn't exist. So let's give an example of that. So here I'm going to draw a jump discontinuity, and let's say that that happens at a, and let's make a guess that the limit is L, which is down here at f of a. This choice was a little arbitrary. You can show that no L will work, but I just picked an L to simplify what's going on here. So notice that if I shrink s small enough, then we can draw our L plus s, L minus s interval. And then you might be able to see that no matter what t I pick around a, so no matter what interval I have around a, there will always be part of the graph that sticks out of that orange region. So in this case, we can say that the limit as x goes to a of f of x is not equal to L. And actually, in fact, it doesn't exist. You can see how no matter what L I pick, I can always do some trick like this. Okay, so let's now do a quick example, a more abstract example where we can't see the graph. So let's see if we can show that the limit as x goes to 2 of x plus 7 equals 9. So as is typical with these epsilon delta arguments, we want to start with some rough work. So let's get an idea of what we actually want to prove. So we want to make the absolute value of f of x minus L, which is just the absolute value of x plus 7 minus 9, to be small. So we want that less than our s. And we want to do so by making x minus 2 less than our threshold of closeness. So we get to choose our threshold of closeness so that this works. Okay, but f of x minus L, which is x plus 7 minus 9, is just equal to x plus 7 minus 9 without the brackets, but that's just x minus 2 in absolute value. So we already know that that should be less than t from our assumption. So maybe if we just take t to be s, then we get our result. We're done. So now let's start our proof, because I think we know how we should do this. Okay, so proof, let s be greater than 0, and that's going to be our arbitrary small number. Then we're going to take our threshold of closeness t to be equal to s. Then, if x minus 2 in absolute value is less than t and greater than 0, then we have that f of x minus L in absolute value is the absolute value of x plus 7 minus 9, which as we saw above is just x minus 2, but we were assuming that that's less than t, and we took t to equal s. So in other words, the absolute value of f of x minus L is less than s if we follow that chain. Okay, but since s greater than 0 was arbitrary, we can conclude that the limit as x goes to 2 of x plus 7 should be 9. Okay, so one last thing. We are using s for our small number and t for our threshold of closeness, but in almost every textbook you'll see epsilon and delta being used. These are the same thing. So our s and t means exactly the same thing. Epsilon and delta are just names. So I'll leave you with a couple of problems to try for yourself. So see if you can show that the limit as x goes to 1 of 3x plus 4 equals 7 using our s and t or your epsilon and delta arguments. And as a slightly more challenging one, see if you can show that the limit as x goes to 2 of 2x squared plus 1 equals 9. Dealing with those squares can be tricky with the limits, so check out this other video that I did where I solve a similar kind of limit, and I talk a little bit about the trickiness of dealing with x squared in an epsilon delta argument.